Hi folks! Welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called electric flux. However, before we get to the electrical phenomenon, we're going to look at a quantity that's called mass flux first. So in this picture, this picture that I've drawn, this represents kind of a side view of a river. So this blue surface up there represents the upper surface of the river, and then here's the bottom of the river. And I went ahead and drew velocity vectors, so the water is moving from left to right. Now, I tried to get them, relatively uniform and roughly the same length. It's not important for the discussion. It's okay to imagine maybe it's a little faster here, not quite as fast here or something, but the relative length of those vectors is not important. What's really important to realize right now is that the water is moving from left to right. All right, now over here, imagine like a hula hoop. And there is a quantity called mass flux that's related to how much water is going through the hula hoop. Now it's important to recognize that right now there would be no water going through that hula hoop in the orientation that it's drawn. However, imagine now that I rotated the hula hoop to like this position. Now we would have a significant amount of water going through that hula hoop, so we would say it has a relatively large mass flux. In this orientation, it has somewhat less flux, and now somewhat less flux, until I get horizontal, and now we won't have any flux anymore, any mass flux. So you'll notice that this angle, very important. Right? Another thing to note is this, that if I could change the size of this hoop, maybe I decrease its size magically, now there'd be less water going through there. So we'd say we have less flux, or we make it larger. Now we have more water going through there. Now we would have a larger flux. All right, so you notice that the mass flux depends on the size of the hoop, specifically the cross-sectional area here. Turns out that the higher the cross-sectional area, the more mass flux we have. Notice that it depends on the orientation of the hoop. If I rotate it so that it was like horizontal like this, there was little or no mass flux. But in the orientation shown, it has a very large mass flux. The other thing is the velocity of the water is a factor. If I could slow this, I dam the river up so that there's no velocity anymore, then we would say that the mass flux to the hoop is basically zero. All right, so when we look at the factors here, area is a factor. I'm going to say angle is a factor. And the velocity is a factor as far as the mass flux is concerned. So I'm going to go ahead now and pause this video and redraw a picture to make it relevant for electric phenomenon. Okay, I'm back here, and what I've done is I've gotten rid of my river, but I've made an example that's kind of analogous to it. So imagine a region in space here where there are uniform electric fields. And I drew one electric field vector pointing to the right, and we can describe those electric fields with what are called electric field lines. And if the electric fields are uniform, our electric field lines look something like this. They would point left to right, they would be uniformly distributed, and they wouldn't be changing in direction. Right? Those are all properties of a constant electric field. Now, imagine that we have a hoop. I'm going to draw it out here. Right? This hoop now, if I wanted to, I could move this into the region that's got the electric field. Oops. All right. Now, if the hoop is in an orientation similar to I have it drawn, notice that none of the electric field lines would really be going through that hula hoop. Very similar to, if those fields represented a river or something, there'd be no water going through the hoop. However, notice if I rotate it now we would have field lines going through this hoop. Now we would have a quantity called electric flux. An electric flux is basically a measurement of the number of field lines that goes through a given area. Notice that if I increase this to an orientation maybe something like this, now we would have a maximum electric flux. If I keep rotating it, the flux would start decreasing until the flux was zero again. Right? So you notice that angle, very important for electric flux. Another thing that's an important factor, the size of this hoop. If I come in here and I make this hoop smaller, we would have less field lines going through it, and hence less electric flux. But if I make it larger, now we have more field lines going through it, therefore more flux. Right? Another important factor is the electric field here. If I could magically snap my fingers and double the field strength, we would represent that with twice as many lines. So we would have more lines, going through our surface here. So the electric flux depends on angle, it depends on the electric field strength, and it depends on the surface area of this geometry. So what I'm going to do here is I'm going to write out kind of a generic expression here for electric flux, and then we're going to get a little more specific with how it's calculated. All right, so electric flux is usually denoted with this symbol, Greek letter phi, and basically it's equal to field strength times area. I say basically. What's important when you're calculating flux is the electric field vector that makes a right angle to the area. So there's going to be a little bit more math coming, but for now I'm just going to say E times A, where the electric field is perpendicular to the A. Right, now what I'm going to do is kind of describe that in a little stronger math sense. So imagine we have some sort of little area here. And imagine that in this orientation, or at this position, we have an electric field vector that points to the, go ahead and draw it in black, I guess. We have an electric field vector in this region that points like this. And it makes some sort of angle here with a direction that I'm going to call the normal. So remember from Physics 1 what normal means. Normal is just a fancy word for right angle. So I'm going to draw a vector that's in this direction, and I'm going to call that the normal direction. I'm going to put that caret symbol, which means that's a unit vector. All it is a direction. Notice there's some sort of angle between the electric field vector, I should have that labeled, and the normal vector. When we calculate the flux through that cross-sectional area, what we would need is the component of this vector that's in the direction of the normal. I'm going to go ahead and draw the vector components in red here. A little longer, I guess. All right. So there is the component of E that's in the direction of the normal. And there is the component of the electric field vector that's oh, pardon me, darn it. That makes a right angle with the normal. Right. So this one right here, that's the electric field vector. Let's say that is parallel to the area. That's not the one we need when we're calculating the flux. This is the one we need. We need the electric field vector that is parallel to the normal. Or we could say perpendicular to the area. That's what I was referring to here when I wrote that electric flux is E perpendicular times A. That perpendicular meant perpendicular to the area. So that would be parallel to the normal. So when we calculate the electric flux, we need the component of the electric field in the direction of the normal, and then we multiply by the cross-sectional area. So if I write that out, noticing that this component is adjacent to the angle theta, we can say that the electric flux, let me draw that in black, is equal to the electric field magnitude times the cosine of this angle. That quantity gives us the component of the electric field in the direction of the normal, right, times the area. Or when we look this up in the textbook, this could be written something like probably EA cosine theta, where again, the theta is the angle between the electric field vector and the normal vector. So that's pretty well it with the electric flux. I'll probably make up more videos with some more math problems, but that's basically what it is. Here's how it's calculated, EA cosine theta. It depends on field strength, it depends on area, and it depends on the angle. Specifically, it's the angle between the electric field and the normal. As far as what it tells us about, it is related to the number of field lines that are going through the area, and we're going to talk about why that's important later on. Hope this video helps. Have a great day.